Okay, this will actually be a two-part video as these notes are pretty long. So let's get started. Okay, so this first slide is a breakdown of two different types of arithmetic and geometric sequence formulas. The first one we're going to look at is explicit formulas. And as you can see, for the arithmetic sequences, the formula involves an addition sign. And the geometric sequence is a multiplication sign. So let's look at the explicit formula. We have a sub n is equal to a sub 1 plus d times n minus 1. What does that mean in words? That means we take the first term, which is a sub 1, and we add it to the common difference multiplied by the previous term, so n minus 1. For the geometric sequence, we have a sub 1 times r raised to the n minus 1. And in words, that means the first term multiplied by the common ratio raised to the previous term number. Let's look at the recursive formula. We start out by stating what the first term is, and then we go on to using the formula. So we have a sub n minus 1 plus d. In words, we are taking the previous term and we're adding the common difference. And as you can see here, I have a ladder, and that's just a little visual for you to think about. When you're climbing a ladder, you need to step on the previous step to get to the next step. And then you're using the previous step to get to the next step. So that's the same thing when we're looking at recursive formulas, is we have to use the previous term to get to the next term. Okay, so we have geometric sequences in the form of a recursive formula. We state the first term, and then we use the formula, r times n sub a sub n minus 1. So again, we state the first term, then we multiply the ratio by the previous term. And that's the recursive formula. Next, we have a few terms to look at. We have the word sequence, and that is a list of things, usually numbers, that are in order, such as 3, 5, 7, 9. Those are odd numbers that go in order. Next, we have the word term or element. They both mean the same thing. So as we, in the previous set of notes, we know that the term is the number that's in a sequence. So 5 is the second term in the sequence above. 7 is the third element in the sequence above. They mean the same thing. Next, let's look at another type of sequence. We have infinite sequence, which goes on forever. And with these sequences shown in this example, you see these 3 dots here. That shows us that the sequence is infinite and it keeps on going. Then we have a finite sequence over here, and that means that it ends. The sequence will end. So we won't have the 3 dots at the end. They'll be the closed brackets. Now we have the word or the term sets, and that's just a collection of numbers. So unlike a sequence, order doesn't matter in a set. In sets, the number appears once. So for instance, we have this sequence example, 0, 1, 0, 1, 0, 1, and so on. It keeps on going. When we state what the set is, we're collecting just the numbers that are in the sequence that only show up once. So we're only going to take the 0 and the 1 because those are the only two numbers in this sequence. So when we say what are the set of numbers, we would say 0, 1 in parentheses or brackets. Okay, so let's go on to, let's see, here we go. The word rule. That's what we use to find the value of each term. So for instance, we have 3, 5, 7, 9 again. It starts at 3 and it jumps 2 every time. But there's a formula that goes to it, and that helps us find the nth term. So if it jumps 2 every time, we can say that 2 times n could be the rule. We could write this rule as 2n. Let's test it out. So we're using 2n as our rule, and we have the terms 3, 5, and 7. 3 is the first term, 5 is the second term, 7 is the third term. So we take the n number and we plug it into our equation. So 2 times 1 is 2. Does it equal 3? It doesn't. We would need to add 1 to make that true. 2 times 2 is 4. That doesn't work out, so we would need to add 1. 2 times 3 is 6, sorry. And it doesn't work out because we would need to add 1 to make it work. So as you can see, it's close, but it's too low by 1 every time. So let's change the rule. Let's try to do 2n plus 1 and see if that works. So we did that up here already. So we had 2 plus 1, it does equal 3. 4 plus 1 equals 5. And 6 plus 1 does equal 7. So it does work. So let's see what the 100th term would be. So we don't have to do all 99 terms to figure out what the 100th term could be, because we have a formula to do that for us. So we do 2 times the 100th term, and then we add 1. 2 times 100 is 200, and when we add 1, we get 201. So that's what the formula is good for. Okay, here's a bit of notation. If you see a letter or a variable with a sub variable, that means it's the term. We're talking about whatever the term number would be, okay? And n symbolizes the term number. So if you were to see, we're doing 3, 5, 7, and you saw x sub 2, that would be, this is the second term. So that means x sub 2 is 5. Okay. And when you see a variable x or a sub n minus 1, that means we're looking at the previous term. So if I were to say, what is the previous term of, over here we have x of the second term, x sub 2 minus 1, that would give us x sub 1. So x sub 1 would be 3. Okay, so this means the previous term. So example, x sub 5, the fifth term in the sequence. Okay, and And that's what we explained up here. Now we have this infinite sequence, 2, 4, 6, 8, and 10. What does x sub 1 equal? So that means that's the first term in the sequence. I look at the first term, so that is 2. What does x sub 3 equal? That's the third term, 1, 2, 3, so that would be 6. Okay, recursive formulas. Again, we talked about recursive formulas. Think of a ladder. So the next term depends on the values of the previous two terms. And the rule for that is x sub n is equal to x sub n minus 1 plus x sub n minus 2. So the previous value and the second previous value. So let's look at this example, and that's going to help us understand this a little better. The Fibonacci sequence is numbered from 0 onwards like this. So we have which number, this is the first, second, third, the 0, first, second, third, fourth, and so on. So the 0 term is 0, the first term is 1, the second term is 1, the third term is 2, the fourth term is 3, and so on. So term number 6 is found like this. So we're using the rule up at the top over here, and it's saying x sub 6. So now wherever I see n in this equation, I'm going to plug in 6. So x 6 minus 1 and x 6 minus 2. Now I solve those. X 6 minus 1 is 5 and 6 minus 2 is 4. So now I go up to my sequence and I say, okay, what is the fifth term in the sequence? That would be 5. And so here's the 5. And what is the fourth term? That would be 3. So here's the 3. So 5 plus 3 is 8. So I look at my sixth term, and it does equal 8. Let's look at the process of writing recursive formulas for arithmetic sequences. Okay, so first you need to determine if the sequence is in fact arithmetic. And the growth factor that's associated with that is the common difference. So you find if it's arithmetic, and then you find what the common difference is. Create the recursive formula by stating the first term, and then state the formula to be the previous term plus the common difference. So that was exactly what we talked about right at the start of this video. So let's find the first 3 terms of the sequence using the following to test the rule. Here's our rule. Okay, so wherever you see n, you're going to plug in what n is equal to on the left side. So here we have a sub 1. So if n is 1, we're going to plug that into the equation. 3 times 1 plus 2. 3 times 1 is 3, plus 2 is 5. Now we do the second one. If n is 2, we're going to plug that in to the equation. 3 times 2 is 6, plus 2, I'm sorry, let's go back a little. Plus 2 is 8. When n is 3, We plug that into the equation. 3 times 3 is 9, plus 2 is 11. So what would the 11th term be? We plug that into the equation. 3 times 11 is 33, plus 2 is 35. Okay. Now let's look at the process of writing a recursive formula for geometric sequences. So we determine if it's geometric, and then we find the common ratio. Then we create the recursive formula by stating the first term, and then state the formula to be the common ratio times the previous term. Because remember, it's recursive, so we're thinking of the ladder. We get to the next step by using the previous step. So again, let's try some examples. We're stating the first term, which is 3. We find the common ratio, here is 2, and then we use the equation. So it's R, the ratio, times the previous term. So let's see. R is 2 times A sub 2 minus 1. And 2 minus 1 is 1. So 2 times A sub 1. A sub 1 is 3. So 2 times 3 is 6. So the second term here is 6. Let's find the third term. 2 times A sub 3 minus 1. So that gives us 2 times A sub 2. And we just found that A sub 2 is 6. So that means we're doing 2 times 6. And that will give us 12. Same thing with the fourth term. We do 2 times A sub 4 minus 1. That gives us 2 times A sub 3. We found that A sub 3 is 12. So we do 2 times 12, and that gives us 24. The process of writing explicit formulas for arithmetic sequences. So we worked on recursive. Now we're going to work on explicit formulas. Determine if it's arithmetic. Then you find your common difference. Use the pattern of the first term and add it to the product of the common difference and one less than the term number. So what does that mean? Let's look at the sequence over here on the left. We have 10, 15, 20, 25, 30, 35. So we see that this common difference is, so D is going to, let me make that cleaner, I'm sorry. So D is going to be equal to 5 because it's increasing by 5 each time. And now we use the formula. So the first term in this sequence is 10. So we see that over here on the right. Then we add, because it's arithmetic, the product, meaning multiply. So this is the product of the common difference. Common difference is 5. 5 times 1 less than the term number. So again, n means term number, and minus 1 means 1 less. Okay, so that is your formula. So here I'm showing you how you get each term in the sequence. So the first term was 10. So I took 10 plus 5 times 1 minus 1 was 0. Okay, so when I solve this out, I do get 10. Now I work with finding my second term. So I do 10 plus 5 times 2 minus 1 is 1. So that gives me 1 inside the parentheses. And so you can see that all the way down, that's what I did. And so let's find the 100th term. Let's do it up here. So you don't have to go all the way down until we get to 100th term. I can use my formula to figure that out. So I state my first term, add it to the product of the common difference, which is 5, times 1 less than the term number. The term number we're looking for is 100. So I do 100 minus 1. Now I solve. So I'm going to do what's inside the parentheses. 100 minus 1 is 99. Then I'm going to multiply 99 by 5. And that gives us 495. And then I add that 10. So now I have 505. That is my 100th term. Now let's see how do we find the explicit formula when we have a geometric sequence. We determine that it's geometric. We find the common ratio. And then we use the pattern of the first term multiplied by the common ratio raised to the power of 1 less than the term number, n. Okay, so we have this sequence over here. We have 3, 6, 12, 24, 48, 96. And using my equation or my formula, I can figure out any term number without having to go through every single one. So I have my first term is 3. And let's see, 3 to get to 6, I'm multiplying because it's geometric by 2. 6 times 2 gives me 12. 12 times 2 gives me 24. So my common ratio is 2. And that we put here in our formula. And we raise it to the term number minus 1. So let's see what that looks like. I've done all the work over here on the left to find each of the terms, but say I want to find the 9th term without finding 7 and 8. So I take my first term, multiply it by my common ratio, and I raise it to the power of 9 minus 1. So now I solve this equation here. 3 times 2, this turns 2 to the 8th. Okay. And 2 to the 8th is 256. And 256 times 3 is 768. So that would be my 9th term. Okay. Partial sums means adding up part, meaning partial, of the sequence. Series is the sum of the entire sequence. So if we have 1, 3, 5, and 7, and they ask for the series, that means you're adding 1 plus 3 plus 5 plus 7, and so on. If they're asking for the partial sum of the first 3 terms, I take my first 3 terms and add them. 1 plus 3 plus 5 equals 9. Okay, so I'm going to pause here And this will be the end of the part 1 of this video.